Welcome to my talk about binary compatibility. Let's get started. So, a bit about me. My name is Marc Mutz. Email address was on the title page if you have questions or want to send in your homework assignment later. I'm a principal software engineer at the Qt company. But for the purposes of this talk, I'm the guy that annoys my fellow Qt developers every 6 months in the API reviews. In particular, I'm not an expert on these matters. It's just the hearsay over the last decade or so, and my involvement in the API reviews, which and then the core libraries, which have kind of made me a bit more well-versed in the matters than your average C++ developer. So about this talk, to manage some expectations, if you need definite answers, go to your vendor, whoever that may be, compiler, STL, even Qt. Because for this talk to fit into an hour, I needed to cut a lot of things out. Also because I'm not an expert on them, but mainly for reasons of timing. So C++ 20 modules solve parts of the problems that we will be discussing here, but not all. Linker scripts can help implement symbol versioning on a lower level than we will be talking about here. Static linking is a completely different kind of linking because there's no really compatibility that you need to maintain because everything is one executable. We'll talk a bit about that at least. And combining different compiler vendors, compiler versions, compiler flags, or libraries compiled with different things into one executable, that is also kind of off topic. Qt tries to do that. It allows you to implement, to compile the Qt library itself with a different C++ version than your user applications, but we have made lots of mistakes in the past about that too, and so that's a best effort basis and not something that we would guarantee. So, overview. I'll start with a motivating example. What is it we're talking about? What is it trying to achieve? Some very small-scale SC and BC problems. Then we will talk about all the definitions that we all know what we're talking about. Then we'll take a brief look at the KDE binary compatibility page. You may think what's so special about KDE. Special is that the ISO C++ committee and the papers reference that page because it's basically the only source of that information in the world. Then we'll talk about a few techniques. And then I would like you to participate in some cheating that I've been starting to do in Qt, and that has greatly relieved our API modernization efforts by allowing us to do things sooner than we would otherwise and traditionally have been able to. And I will talk about Q&A if we get time. I have 100 slides, so I may be going a bit fast. So, example. We are releasing a small library. It has this function, scan, takes an int, fd, and returns an int. And then we release the next library version, and somebody asked for options to scanning. Right? So we have an enum class, options, and we can now pass options. So at face value, everything is okay because we can recompile an application, and if it worked before, if the options are correct, not changing something if you pass empty options, based on the version 1.0 behavior, everything should be peachy. But, of course, this is binary incompatible because we changed the function. I will talk a bit more later what changing the function actually means, because there are parts of the function that you can change and some parts that you can't to keep it binary compatible. But adding an argument, even if it's defaulted, is binary incompatible. Right? So a library, application that's linking against our library. When we exchange the v1.0 against the v1.1 without recompiling, we will get a linker error because the function has been renamed, right? So we need to release a patch version. And we now know that we should not touch the old function because old code is relying on it. So we use overloading. Right? So everything is peachy. The old function has been unchanged, and we have added an overload that is called when you actually give some options. So only new code will call this. So everything should be peachy. But we again get a bug report. Now it's source incompatible because somebody is passing our scan function to an STL algorithm, thereby taking the address. And now we have an overload set and not a single function anymore. So we just broke that code. So we need to release a second patch release. And we start with what we want to have. That's this. That is what we want to have going forward. And that's what we need, sorry, the first line is the one that we need to have for the old clients. At least in the ABI, in the application binary interface. We will talk about all these definitions. So this is what we have and what we must have. So what we want is some magic that appears, and that will give us the best of both worlds. It will give us the API, which only contains this function, and an ABI, which contains both functions. And the rest of the talk is about how to get there. Okay? So, definitions. I'll briefly talk about Qt and KDE, about BC, binary compatibility, and SC, source compatibility. If there's a small I in between the two letters, it means incompatible. So SIC means source incompatible. We'll talk about what's an ABI, what's an API. We'll talk about forwards and backwards compatibility. We'll talk about name mangling and exported symbols. So Qt is a cross-platform environment written in C++, so that is kind of pertinent for this conference. KDE is a Unix desktop environment based on Qt. Most of you will probably know these things. Both of these promise and have promised for at least the last 20 years binary and source compatibility within major releases, right? So we have quite some experience. And that doesn't mean we were perfect and never made our BC and SC mistakes, and we grant ourselves some source incompatibilities. But I think we have quite a bit of experience in this. So this definition of binary compatibility is right from the KDE wiki. A library is binary compatible if a program linked dynamically to a former version of the library continues running with newer versions of the library without the need to recompile. So let's take this apart. The first thing that we see is that we need a library. A fully linked program cannot be binary compatible. You need two things. You need a library that can be binary compatible. You need to have a program that links against it dynamically. You can also ask for static binary compatibility, and people do, but it's a completely different beast because when you link dynamically, you have multiple executables that are at runtime linked together to form a single process. When you have static libraries, you have object files, essentially, and that get linked together. So you're just compiling different parts of the application at different times and then link them together. So you don't have this executable boundary in between them, and that makes talking about binary compatibility a completely different beast that we don't go into here. Then that's the C in BC, is that you link to a former version, to build your program against the former version. Then you replace only the library, and everything should work. Yeah? So that's the C. And the fact that we don't need to recompile, that we just dump the SOs or DLLs into the directory and start up the application, everything will work. That's the compatibility. That's the binary part of the compatibility, right? So here's the sentence again. Some observations. As we've seen, KDE at least does not define what BC is for static libraries. That does not stop people from trying. And continuous running is pretty vague, right? That it still links at runtime, that I don't get missing symbol errors, that's a necessary condition, but by far it's not a sufficient one, right? There's something called behavior compatibility, Hiram's law, all these nice things. Even a bug fix can break an application, right? Fixes 100 applications, but breaks one. So it's a bit more complicated. That's why the KDE wiki is a bit loose on that. So we will focus on the still links part here. Another observation is that while we talk about library, it's not actually a library which is binary compatible. A type can be binary compatible, and a function can be binary compatible. The library is just a shipping vehicle, the smallest shipping vehicle that you have in which to talk about compatibility. The binary compatibility itself is a local property of types and functions. And it's also important because in API reviews, you can go look at classes and overload sets, and you can locally decide whether they are binary compatible or not, or source compatible even. Right? If you had the whole picture to keep in mind, that would be much harder. So that's good. The definition of source compatible is if a program needs to be recompiled to run with a new version of the library, but does not require any further modifications to the source code, the library is source compatible. So that's what you usually expect from your libraries, that the new version does not break your source code. Some observations. Inline library code can be source incompatible, but it's usually not binary incompatible. Why? Well, that code is compiled as inline code into the library user and resides there. So if I replace the dynamic object under the hood, I'm not replacing the inline code that was compiled into the application. And that's one of the actual main parts of the talk. Binary compatibility is not the same as source compatibility. API is not the same as ABI, and you can vary the two independently. We have already seen examples where one is true and the other is not. For example, if I add a default argument to a function, that's source compatible. All existing callers will continue to compile, but it's not binary compatible. And if I add a new overload, that's binary compatible, but it may not be source compatible if somebody is taking the address. So what's an ABI? You can get very, very technical and very, very detailed. For the purposes of this talk, that's what the linker sees, right? It sits below C++, so C++ does not actually say much about, if anything, about linkers. It deals in the mangled names, not the names that you see in the program, and in exported symbols. And an API is that what the compiler sees, right? That's what the ISO C++ standard actually defines. There you have overloading, which you don't have on the BC level, or on the ABI level, because of name mangling. You have unique names for everything. You have defaulted arguments, which don't participate in the ABI. You have type def. Type def is something that's purely on the source level. Right? In the binary executable, you will always find fully qualified names. So then backwards compatibility is your normal compatibility. I have a code compiles an old library, and that continues to run against a new library. Yeah? And Qt, for example, provides backwards SC and BC in major releases, so from 5.0 to 5.15 and from 6.0 onwards. As I mentioned, we do take a few things that we allow ourselves to break your code, like removing an unused include file from a header. If you transitively rely on those includes, you better add them explicitly to your own TUs. We allow ourselves to add overloads to functions. So like the standard library, we're not really allowing you to take address of our functions unless there are slots where this is part of the API. Forwards compatibility is kind of the reverse. Code compiled against a new library continues running against an old library. You may not have seen this anywhere, but Qt provides this in minor releases. So if you have code compiled against 5.15.19, it will, also we're told, run against 5.15.0. This is good if you have a bug and you want to bisect where it appears. You don't need to bisect on the source code level and rebuild Qt all the time, but you can bisect on the library version level, right? So that's why this is important. Of course, if you use new features, like new platforms that are supported, we have enums for all the platforms. If you use those in your source code, then of course you cannot go back. But if your code compiled in a .0 release, and then you compile it against the latest release, and then go back to .0, it should work. So name mangling. Name mangling is the process of creating unique names from overloaded functions. Because on the ABI level, on C level, there is no overloading. Right? The functions are only distinguished by their names. Kernighan-Ritchie C does not even distinguish them on the arguments. Right? You can have the same function declared with different arguments, and the C compiler will happily accept that, because that's what the binary level is all about. So in order to do that, it encodes the things that you can overload on, which is the name, including any scope. It's the signature, which means the number of type of arguments, including template arguments, and including CV and L value, R value qualifiers for member functions, the stuff at the end, right? So what it does not encode is the argument names and the default values of those arguments, if there are any. Top-level CV qualifiers, so foo of const int is the same as foo of int, unless you're working still on SunCC, where it's different. No except is not part of the name mangling. And the access specifier, so if I'm using public, private, or protected in a member function, that is not part of the name mangling, unless you're on Windows, then it is. And the return type. So I can't overload on return types, so it doesn't make sense for it to be included in the mangling, unless you're on Windows, then it is. Right. So conclusion for name mangling, a change to the name mangling inputs, which vary from platform to platform, keep that in mind. That's an ABI break, because if the mangling changes, the name changes, and then the symbol is not found. Change to non-inputs to the name mangling should be binary compatible, unless you're on Windows. Yeah, always keep the platform differences in mind. So exported symbols. On the C++ level, we know our three linkages, right? We have external linkage that you use when a function is defined in one TU and another TU should be able to use it. So you put the declaration in a header file, and duplicates are not allowed, so you get multiple definition errors from the linker, right? Then you have static linkage, where only this currently compiled TU, translation unit, can see this symbol. And if you have a static function in a header, every translation unit that includes it will have a copy of it. Yeah. And duplicates stay. Each TU will have its own private copy of that. And then we have internal linkage, which is kind of mixture between. Other TUs can access it. That one is not just the declaration that you need, but also the definition, of course. And duplicates are merged. If I have two TUs that use the same inline function, the linker will then merge the two duplicates into one at link time. At the DSO level, so dynamic shared object level, we have basically what is callable from outside and what is not callable from outside. And that differs between Unix and Windows as usual. Windows differs. So callable from the outside is always inline code. But that's not really calling into the library because it's copying the source code or the binary code from the header-only library into my own executable. That's not why we would link dynamically to use an inline function. On Unix, by default, all external functions are part of the interface of the DSO. On Windows, not. So alternatively, you can say on Windows, unless you do something, by default, you can call nothing from the DLL. And on Unix, by default, you can call everything. So exporting, then, is the process of reducing for the Unix side or extending for the Windows side the set of callable symbols in the DLL/SO/DSO. Yeah? On Windows, you know declspec, the DLL import-export. On Unix, you need to first change the default visibility to hidden, and then selectively you can make certain symbols have default visibility again, which means they're callable from outside. These attributes need to differ for when building the library, and this needs to be DLL export, and if you use the library via a header, it needs to be DLL import. So everybody knows that you hide them behind macros, and those macros then switch between the two depending on whether you build the library or you use it. So in Qt, that macro is called Qt module export, for example, Qt core export, Qt network export, and so on. We let them generate by CMake because if you have such a complex thing, you should use it for something good. So, types don't actually need exporting. Functions and variables do. But you see exported classes everywhere, right? That looks like this. You have the export macro between the class and the class name. But that just means export all the members, all the functions, all the variables. Right? It's just a shortcut. And one of the important things that you want to export is the vtable of polymorphic classes. You can also have them inline. When all the virtual functions are inline, then also the vtable will be inline. And then you can hope that the linker collects them all. But we'll see, or we'll link. That's one of the things that I don't have time to talk about. We will link to the article that shows you what happens if you have inline vtables. So wholesale, I call this wholesale exporting the class. What does it export? It exports all the member functions. It exports all the static data members, including the vtable. And also inline functions get exported. And on Unix, that does not really have a difference. But on Windows, that means that even the DLL version gets called. And this would not be Windows if it was so simple, unless the compiler decides to inline the function actually into the application. Yeah? So you don't really know. And wholesale exporting the class is recursive. So if you have nested types inside the class, that process is recursively constructed. So if you have marked the outer class, all the inner classes are automatically exported too. So what it does not export is friend functions, at least hidden ones, those that are defined inside the class body. Non-static data members, because they are not variables. Member function templates, because they are not functions. And nested class templates because they're not classes. Yeah. They're templates. So conclusion, you don't want to export inline symbols because then they become part of the ABI, and we use inline functions partly because we want them to be part of the API but not the ABI, so we can change them more easily. You want to selectively export external symbols, those that actually need called from outside the DSO. And you want to avoid having an inline vtable, and there's a link. And later in the references, when you download the slides, there's an article of mine, What Can Go Wrong. So the golden rule of class exporting is export polymorphic classes wholesale, because unfortunately that's the only way to export the vtable. Yeah. Define the destructor out of line, even if it's empty or equal defaulted, because that pins the vtable to a single TU and actually makes it exported and not inline. And do not wholesale export non-polymorphic classes. Export individual functions and variables only. For example, don't export inlines, or don't export private functions unless they're called from public ones or from inline code. So, why? Why these rules? Exported symbols are part of the ABI. Non-exported symbols are kind of private, library private API that cannot be called from the outside, so there cannot be a BC issue with them. So we want to minimize the exposure for BC problems. So fewer exported symbols, fewer BC headaches. And you want to have something like library private symbols. That's actually something that modules should allow you to do. So a note on unexported inline symbols. The linker deduplicates them only per executable. And we have said that if you dynamically link together a shared library and an application, that's two executables that are linked together. The linker, as the one that's running after the compiler, not the one that's running before the execution of the program, that's the dynamic linker. The old linker does not know those two components until the dynamic linker sees them both. Yeah? So it cannot physically remove duplicates. It needs to leave at least one copy of each inline function, of each inline variable in each executable. And that means that each executable that has a call to an inline function or a reference to an inline variable has its own copy. That's usually not a problem for functions because it does not really matter which one you call unless you have a difference between the library, which has a newer version, and the application, which has an older version of the inline code included. Except that the addresses differ and you compare them. But it's surprising for variables because instead of one singleton, you suddenly have 2 or 3 or 4, right? So that's something to keep in mind. The solution here is aggressive GRI or scary. Scary, you know, is that title from the paper from Bjarne, where he's extracting non-template dependent entities from a templated entity in order to reduce the number of symbols. And DRI is don't repeat yourself. So in other words, extract things like that, inline variables into separate functions, and then pull those functions behind the ABI boundary, meaning make them out of line and export them. So you don't end up with multiple copies. So here we are quickly looking at the KDE BC page, if we can get this over. Yeah. So here's the content. I can't see it actually, but so we have the definition, which we just copied. There's some talk about ABIs, which talks about Itanium ABIs. Nothing in this talk is about any specific ABI. Then there's the do's and don'ts. Then there are some tricks that we'll also talk about. And then there are tools that you can use if if you've already fallen into the trap of not providing for future extensibility. And in the do's and don'ts, there are some interesting things about enums. Did you know that if you add an enumerator to an enum, it may change the underlying type, and then it's binary incompatible? Right? There's fun stuff like overriding a virtual function that has a covariant return type, which is binary incompatible if the covariant return would change the pointer value. Yeah. And then my favorite is down here somewhere. Yeah, here. You just have multiple inheritance. I don't have internet. Yes. You have multiple inheritance, and if you add, where is it? Should be here somewhere. If you see multiple inheritance, shout. I don't know why it wants to look up an internal link. I don't know. Well, okay, suffice to say that there are things that you just don't have in mind when you code your everyday. And that's where the API reviews come in, where we need to catch these things, hopefully. So, let's go. Does this work? Yeah. Okay. Let's talk about techniques. I don't really have time, so I will very quickly go through them because you should be familiar with them. The first one is Pimple, pointer to implementation. All I will say here is that I have written extensively on Heise and on my own blog about these, so you can have a look at that. Another technique is reserved fields, where you have either an explicitly reserved void pointer for later storing more information, or you have unused bits in the bit field, or you have reserved other fields, or you make padding that you anyway have in your type explicit in the hopes that you can later use those holes to fill with actual active data variables. You will need them maybe unused because Clang likes to warn if you don't actually use them. You need to initialize them because if you don't, then you get random garbage, especially if it's initialized or not initialized from inline code. So I will skip that. So this I need to talk about. So move semantics. We want move semantics to be a faster copy. So they should be fast. So that calls for them to be inline, especially if it's just shuffling pointers around, right? But on the other hand, they should not break binary compatibility. So how can I make an inline move constructor or move assignment operator if I'm using the Pimple idiom, right? Is there a conflict of interest here? And the answer is no. Because the natural implementation of move assignment can be inline. It's just calling swap, and swap can be inline. It's just swapping memory. It does not need to reach into memory. It does not need to run constructors, destructors. Yeah? So swap can be inline. If you can construct, if you can define the member type as a direct data member of the class, which means it needs to be complete, then you can swap it. Yeah? And if not, then you have a pointer and you can swap the pointer. So that works for Pimple and reserved fields alike, actually works for all the data members. And it even gives you the ominous valid but unspecified state, because you start with two valid states, you swap them, both are still valid, right? But in this situation, assignment does not destroy the left-hand side. That's okay if you just have memory resources. It's actually beneficial if you swap two strings and the capacity is not discarded but stored in the moved from object. But it's not okay if you have, for example, a mutex locker and you expect that if you assign over it, then the mutex gets unlocked. And if it's just swapped out into the moved from object, which may live for another X seconds, That's not good. So in that case, you can use the alternative move and swap, just like copy and swap, because it's implemented in terms of copy and swap. Those can be inline. So the move and swap idiom can be inline, but then needs a move constructor. So far we've talked about the move assignment operator, which is easier. So the move constructor also has a natural implementation, which can be inline. It's a halfway swap. It's standard exchange. Yeah? I just dump an initial 0 value into the other, into the moved from object. Unfortunately, that brings me back to my favorite topic of partially formed states. So if you have a nulled D pointer in your pimpled class, you need to define what the null pointer means. And the easiest is to make it partially formed. So you cannot do anything with the moved from object. You can destroy it, okay. And you can assign a new value, okay, but you cannot call any other member functions. There's a talk at this conference from 2020, which is also in the references, which goes into details there. So the problem with that is that standard exchange in inline code does not work with smart pointers. So if you have your pimple, a raw pointer, everything's peachy. But if you want to use, for example, a unique pointer, you will get a compile error, or not a compile error, a linker error, or compile error actually, yes. Because the compiler wants to call the data member destructor. And for the life of me, I cannot know why. So if you know, please come to me and tell me. There's no reason why it should do that. It doesn't need it, but it breaks encapsulation if we would allow it. Because the destructor of the unique pointer, of course, needs to know how to delete the payload object. But we don't have that information in the header. So ISO C++, can we fix this? Can no expect move constructors please not call data member destructors? I don't know why they should, and it's a major pain in the ass, especially since MSVC, again, does not play ball. So as a workaround, what we've been doing is we have the destructor of the smart pointer call an out-of-line member function. If you compile that stuff, you will see that in the compiled move constructor, there is no call to that function because it's not needed, but the compiler wants it. So that's a trick to use. Unfortunately, MSVC, when you enable link time code generation, it tries to look up that symbol because it wants to optimize it before optimizing call. I don't know why. We call it a bug. We don't support this because allowing this would mean that we expose which smart pointer we use for managing our pimples in the ABI. And we don't want that. We want inline move constructors, yes, but we don't want to pay the price that we lock in which pimple pointer we actually use in the implementation in our ABI. So, conclusion. Move, SMF, special member functions, and swap can and ought to be inline. And ISO C++ and MSVC may have some bug fixing to do because I don't understand where the destructor is hiding. So another technique is virtual hooks. I'll just very briefly show you how this looks. So it asks you to add this implementation to all of your classes in the hierarchy, because then you have a virtual hook, as the name suggests, that you can then later use to implement new pseudo-virtual functions. Yeah? Here's the call side. We package the arguments and the return value together into a void star. We have some kind of ID that describes which operation we are doing here, this pseudo-virtual or some other pseudo-virtual that was added earlier or later. Then we call the virtual hook, and then we return the result that we've gotten back in the first member of the array. And in the virtual hook, we then check for the ID to match and then perform the asked for operation. Yeah. This is basically replacing n virtual functions with one in order to not have to add virtual functions. So the problem here is that you need to add that ante hoc. That means before you find the need to extend your API with a virtual function, you will need to have added that virtual hoc before. That's always bad because we're not so forward-looking. Then inline namespaces, I'll also skip that because I want you to cheat. So let's talk again about separating API and ABI. First observation is that types don't exist in the ABI, right? Only as a collection of functions acting on their memory locations. So there's no point in the ABI, there's a name mangling for it, but there's nothing that represents the type itself. There's only an agreement of certain functions as to the type and location of the points fields. So ABI is maintained as long as the existing memory layout does not change and as long as the existing functions are not removed. We can add existing functions. Theoretically, we could also tag new fields at the end if we control all the functions that act upon them, but traditionally in C++, you would create objects on the stack. Then you need to have the size, and you cannot have the size change from one version to the next without recompilation. So that's out of the question. So here's a side-by-side comparison between a point class and its ABI, right? So the member functions are reflected by the known offsets that they have. Yeah? And then we have the name mangled functions. Point set x takes an int, point x returns takes void star, takes void, set y and set x, set y and return y. So this is just my version of name mangling, of course. If you can write it in C++, it's not valid name mangling. So now we want to add, or we want to change the set y function to take a long, because we want to catch overflows. Yeah, we want to catch we want to take the widest possible type, and then do the range checking internally, and only then assign to the variable. The old API would do the truncation at the call side outside of our control, yeah, just as a motivation. So I want to replace that function. Yeah, I can add it, no problem, but it's no source incompatible, as we know. Not only because I can't no longer take the address of the function, but because calls that don't give an exact int or exact long will now be ambiguous between the two calls. Yeah? So again, what I want to do is I want to replace the function. I don't want to just add one, I want to replace it. And I can, of course, comment out the old function, but then it's also gone from the ABI, and that's binary incompatible, so we can't have that. So we want, again, magic removed API only, that we can slap on this function, and that magically removes it from the API, but keeps it in the ABI. Now we've come full circle to the motivational example from the beginning, right? So how to do that? So I take my point CPP, where both of these functions are currently implemented, but I don't want to release it like that because it would be source incompatible. I add a new translation unit. In Qt, we call them removed API for reasons that will become apparent in a second. So now I'm defining in that TU magic removed API only to 1. Are you seeing where this is going? Yeah. Then I include point.h. So this TU actually sees both overloads. And if I assume that magic removed API only is set to 0 undefined, for all other TUs, those will not see the old function. They will only see the new function. So now this, of course, does not compile anymore because point.cpp, as I just said, does not see the old overload anymore. So I need to move it over into the new TU to implement there. And of course, I implemented just casting and calling the old function. So let's do that. Yeah. And that's it. That's literally it. So you can get fancy, and we did, and version the whole thing. So you can say this was removed in Qt 6.2, 6.3, 6.11, and so on. You need this macro per library. So we have Qt core removed since, Qt GUI removed since, and so on. So we let the build system generate all this stuff for us so that we don't need to. Like the export macros, we also let CMake generate them for us. But crucially, you only need one removed API.cpp per library. And that's the new thing. We had this in Qt 4 because we were inheriting from our template containers, and the template containers had two different variants of iterators, checked and unchecked iterators. And depending on whether you ran with one or the other, the linker would not find the other one, so we needed to have one TU where we compiled with one version of the iterators and another one with the other version, so that would be exported from Qt Core for use in Qt GUI. But we don't need all this anymore because now we have this general mechanism. So of course, more sophisticated symbol versioning exists. For example, glib C uses that. And I would not be surprised if libstandard C++ does not also use it. The advantage here is that, as I've just proven, I think everybody understood how this works. So I can tell this to a C++ developer without deep linker knowledge within an hour. It's cross-platform. It does not depend on whether it's an ELF or a DLL executable. And the important part is it works post hoc. It works after I've went into the trap and cannot get myself out. And before, we would need to add an overload, add a comment, hash Qt 7, remove this overload. And then you would come Qt 7.0.1, and you would find that the overloads are still there because nobody was cleaning them up. And this guarantees that it's automatically cleaned up. So homework for you is use that removed since to remove a no except from an exported function again. Think about the syntax, what to put in the header, what to put in the removed APIs.cpp, but also think about the syntax. What does it mean to have an exported, released function that was no except, when we now drop the no except? Okay? And what we've used this for is we have the versioning information, so we can set a cutoff version, like literally set removed since to 0 for all the versions before a given version. And what we have done is we just introduced a user configurable cutoff version for the ABI zombies that we have living in the DSO. Yeah? In other words, we have a configurable rolling binary compatibility window, where the upper bound is the library that I'm compiling, that I'm building against, and the lower bound is the set of the cutoff version that I've set when I've built Qt. And there's a config option in Qt. The biggest drawback of this is that it does not work for virtual functions. You cannot add virtual functions, therefore you cannot replace virtual functions, because replacement is adding and then removing. And if it weren't for virtuals, and we have quite a few of those in Qt, unfortunately, Qt could stay another 2 decades on Qt 6.0. Right? Alternatively, Qt 7 could be binary compatible with Qt 6, but we have those stupid virtuals, unfortunately. So, key takeaways. The ABI is not the same as the API. Both can vary independently of each other. Qt has introduced a user configurable rolling binary compatibility window, and so can all of you. And the biggest impediment to ABI evolution is wholesale exported classes and virtual functions. So we have, according to my clock, 10 minutes of for questions. Alternatively, I have bonus slides. Do we need a microphone?
Yes.
Oh, there we go.
Thank you. This might be part of this expert thing that we are not supposed to ask about, but I still just want to double check. Like, you were talking a lot about virtual functions in this binary compatibility talk. But as far as I know, from the standards point of view, a vtable does not even exist. So when we're trying to think about binary compatibility between compiler versions or between different compilers even, do we have guarantees that vtables across those boundaries will still work? And where can I find those guarantees?
So the place where these things are defined is the platform, or in case of Windows, there are multiple, the compiler ABIs. Right? We've seen the reference to the Itanium ABI, which was developed for the old Intel thingy, but which is used by GCC across all the platforms, including MingGV on Windows. So you can't link MSVC and MingGV code together on Windows because they have different ABIs. And likewise, ClangCL will need to use the MSVC ABI. Right? So that is, in the case of Itanium, there's a real detailed document about this that includes calling conventions, where in function calls registers, which registers are used for function parsing, which registers need to be cleared by the caller, which will be cleared by the callee, where's the return value going, and so on. Right? So that's the ABI. That's where all this is defined, and also the layout of virtual function tables. There's a question at the end.
Yeah, actually, it's a follow-up question related to the ABI guarantees with virtual functions. I was under the impression, at least with if you have a pure virtual interface, that on Itanium and Windows you can add new virtual functions as long as you don't change the order. I'm curious what you know about this, and if that's actually true, or if I just been getting away with something by luck.
So if you have a pure virtual interface, you have a virtual function table. And if your pure virtual interface has 5 functions and a destructor, then you have 6 or 7 slots in the virtual function table. Yeah? If you then implement that interface in a separate library, yeah? And only then we can talk about, or in an application, only then we can talk about binary compatibility. Then that re-implementation, or that implementation adds another virtual function. Yeah? Where will that virtual function be represented in the vtable? At offset 1, 0 from the base class. If the base class gets a new virtual function, it grows, and then the compiler will override, in the best case, of course it's undefined behavior, so anything can happen. In the best case, it will override the derived class new virtual function pointer into the base class virtual function table of the new virtual function. So no, it's not binary compatible. And I don't think that it ever worked.
Is there some possibility of automated testing of BC and SC, or some existing tooling?
So what exists is scripts that even output nice HTML tables, where you see, where you basically give 2 DLLs or 2 SOs or 2 dlibs, and it compares them, and it shows you a binary diff. So it shows you which functions have been added, which functions have been removed, yeah? And ideally, there should not be any removals. I don't think it shows you, but I guess one could extend it, the size of enums, the size of types, and so on, which also must not change. So yeah, we've used those things in the past. I don't know why we don't anymore. But yeah, there are scripts that give you at least a binary diff, so that's easier than just going to all the implementations. You would still need to check, is this a re-implementation of a virtual function in a class, in a derived class that did not have that virtual re-implementation, which has behavior problems. You can read up on that in the KDE BC page. So it may or may not be binary compatible, depending on the actual implementation. So such a tool cannot give you a definite answer, but it can be a great help to flag where changes were made. Sorry, I don't know what the name of that thing.
I know you initially said you wouldn't talk about static linking, but can you just give a short summary what would change basically with static linking?
Yeah, so what the advantage that you have with dynamic linking is that you have these executables, which you can look at in isolation, because neither the compiler nor the linker will see them until they're finally composed. What this gives you is you can completely ignore ODR violations, because ODR violations are only defined for a single executable. Yeah? If they were valid for the whole program as dynamically linked, I could not add a new function to an existing class and without recompiling. But that works in practice, and we're using it all the time. So de facto, if not de jure, that is not an ODR violation. So one thing that I did not show, it's on the bonus slides, is we can use this mechanism that I just showed with a bit of extension to inline functions that are formally out of line. Yeah. In which case...
Can you show that?
Yeah. So in that case, all the callers outside of the library see the function as inline, and both removed API.cpp and all the other TUs that make up the library need to see it as out of line, because otherwise you have a ODR violation. Yeah? If one of them would see them as inline, you may end up with, well, it's an ODR violation. Anything can happen, undefined behavior, right? So this is one very obvious example where I can't just remove it for one TU. I need to take into account all the TUs in the library. And if my library is statically linked, that extends to the whole application, because the linker sees everything. And it tries to remove all the duplicates of all the inline functions, right? So we had a bug report about that, and we needed to change our macros a bit, that in static linking we completely disable this thing. If we're building for static, there's no binary compatibility in static linking. And the linker will remove everything, not only inline code, but also external code, static code, linkage code that is not used, it's removed, right? So in that case, it's... but yeah, if you have, so inline functions. So how to make formally out-of-line functions inline. The idea is to use remove sins to remove the out-of-line function while keeping it in the ABI, and then adding the inline function like we did with the changed parameters. There are two problems. The first obvious problem is that the two don't overload, and I think I forgot to mention, but it's kind of obvious. In the removed API.cpp TU, both overloads are visible, and you cannot have one function be inline and the other token for token identical be not inline. So that can be solved by hash else, right? You have if removed since else, yeah. So that is easy to solve. The other one is what we talked about, ODR violations. Removed since also has ODR violations, because I'm pretending that one function exists in one TU and it does not exist in all the other TUs. But that is not actionable. But if I have one function be inline and then the next to it's extern, or even exported, and in the other one it's inline, that's very not much actionable because the compiler gets to see those and to process those. And so we have 3 domains, as I said. We have the removed API.cpp, we have all external callers to the library, and we have all the internal callers of the library. External users should see the function as inline, that's what we want to achieve. Removed API must see the function as out of line, otherwise the function does not end up in the API. And internal users, because of ODR, must also see it as out of line. Yeah? Because it's linked together with removed API.cpp. So this is the API that we have in Qt, or a slimmed down version of it. You slap an API inline since on top of the function in the class body that you want to inline. And you copy the inline implementation out of the CPP file into the header file and put it in between if RP inline impl since and end if. And in removed removed API.cpp, you just need to include the header. Everything else is done automatically. So how does this work? This inline macro expands to inline for external callers and to nothing within removed API.cpp and for internal callers. Right? So for external callers, the function is marked as inline in the class body. Implementation is out of the body. So it's inline. And then we need to make sure that the definition is not visible for internal callers to not run into undefined and multiple definition problem. So the inline impl since is defined to 1 for external callers and for removed API, because both of these need to see the body of the function. One to be able to inline it as an inline function, and the other one to be able to compile it into the API. And other internal callers outside of removed API must not see the body, so it's diffed out. And that's then.